This is Group 7 from MECH 300, Thermodynamics 2, example refrigeration cycle. So in this example, we have a refrigeration cycle, which is shown right here, and it tells us that the compressor inlet is saturated vapor at 32 degrees Fahrenheit, and the exit of the condenser is saturated liquid at 110 degrees Fahrenheit and 160 psi. The working fluid in this problem is R31A, and it says it is flowing at 678 pounds per second. It is asking us to find both the cooling load and the coefficient of performance with a compressor efficiency of 78%. So to start off, we need to find all of our enthalpy values, and so we can get those from table A10E, and to get our H3 value, we just need to go to the saturated liquid value at 110 degrees Fahrenheit. And so at that spot in the table, our H3 is going to be equal to 47.81 BTU per pound. And that is at saturated liquid. So we'll put that in. And because from states 3 to 4 we have a throttle, our H3 is going to be equal to our H4. So we can just pull that value right down and put it in for H4 as well. Now, in order to find our H1, we will also go to this table A10E, but we will need to interpolate between 40 degrees Fahrenheit and 30 degrees Fahrenheit in order to find our values at this 32 degrees Fahrenheit here. So when we do that, we're going to have 40 minus 32 over 40 minus 30 is equal to 107.39 minus our enthalpy value at state 1, and that's going to be over 107.39 minus 106.01. And when we run that, we will get our H1 equal to 106.29 BTU per pound. So we can throw that up in our table. And we are also going to need our entropy value at state 1, and we're going to have to do a very similar interpolation. And so to find that value, we're going to have 40 minus 32 over 40 minus 30 again, and that is going to be equal to 0.2189 minus our entropy value at state 1, and that is going to be over 0.2189 minus 0.2196. And so when we run that, we are going to get our entropy value to be equal to 0.2195. So we can throw that up in our table at state 1, and then because this is isentropic, we can assume that S1 is going to be equal to S2, so we can pull that value down as well. So to find our value at state 2, we first are going to need our pressure at state 2, which since from state 2 to 3 it is a heat exchanger, we can assume constant pressure there. So our pressures at state 2S and at state 2 are both going to be 160 psi as well. So to get our enthalpy value at state 2S, we're going to have to go to table A12E, which is a superheat table, and we're going to need to look at 160 psi and then this 0.2195 BTU per pound Rankine entropy value, and we're going to interpolate for our H. And that is going to look like this. So we are going to have 0.2209 minus 0.2196 over 0.2209 minus 0.2157. and that is going to equal 118.89 minus our enthalpy value at our state 2, S, and then that's over 118.89 minus 115.91. And when I ran that, I got 118.15 BTU per pound. So we can throw that up in our table. And then we now need to find our actual enthalpy value at state 2. And to do that, we are going to use our compressor efficiency, which was given to us as 78%. So we are going to use the equation. Our compressor efficiency is equal to H1 minus H2S over H1 minus H2. And so that is going to look like this. So we're going to have 0.78 is equal to 106.29 minus 118.15, and that is going to be over 106.29 minus our H2 value. And when you solve that equation, you're going to end up with H2 equaling 121.50 BTU per pound. So now we have all our H values, so we can start thinking about solving for what was asked of us. And so in part A, we are asked to find the cooling load in tons. And so to do that, we are going to use the equation Q dot in is equal to M dot times H1 minus H4. And so we just found our H1 and H4, and our M dot is given to us Our M dot is given to us as 678 pounds per second. So we have everything we need to solve for this. So this is going to be 678 pounds per second times 106.29 BTU per pound minus 47.81 BTU per pound. And when I ran that, I ended up with 39,649.4 BTU per second. But it asks us to solve for it in tons, so we're going to need to convert BTU per second to tons, and that can be done using this conversion. So there are 12,000 BTU per hour in 1 ton. So that'll cancel out our BTUs, but we still need to get rid of our seconds. And so to do that, we use the conversion 1 hour is equal to 3,600 seconds. Now we'll get rid of our seconds. BTUs cancel out there, and our hours are going to cancel out there. And then we are only left with tons. And that comes out to 11,894.8 tons. And so we are done with part A. And part B asks us to find the coefficient of performance. And so to find our coefficient of performance, we can use this equation. Our coefficient of performance is equal to our Q dot in over our W dot of our compressor. And so that is going to equal M dot times H1 minus H4 all over M dot times H2 minus H1. And our M dots are going to cancel here, so we are just left with our enthalpy values. So we can plug in those which we solved for earlier to be 106.29 minus 47.81, and that is going to be over 121.5 minus 106.29, and that comes out to be 3.84 for our coefficient of performance. So just a quick recap. In this problem, we were given a refrigeration cycle, and we were asked to find the cooling load in tons and the coefficient of performance. And so we took our H3 value from the saturated liquid value in our table. We interpolated to find our H1, and then we used our entropy value and our pressure to solve for enthalpy at H2S, and then used our compressor efficiency to find H2 actual. And then we used those values and plugged them in to our equations below to solve for both our cooling load in tons and our coefficient of performance. Thank you for watching.